difficult. So Newton's method is one of those ones that allows us to figure out roots with a whole bunch of busy work. So a little known fact is that if you have a polynomial of degree 4 or less, you can probably find the roots fairly okay. But anything larger than that, you pretty much can't find them very easily. Newton's method allows us to find these roots. So when we're talking about Newton's method, it is a bunch of busy work where we're going to be doing derivatives and plugging stuff into derivatives and then dividing by numbers, and it's just busy work. So let's assume that we have some root. In other words, it is a value which makes this equation equal to 0. It is not necessarily a number in which it is crossing the x-axis. When we talk about roots, they're not necessarily x-intercepts. They are values that make this thing equal to 0. So let's assume we have some root r, so that when I plug in r, I get 0 out, and we'd like to approximate it. One of the ways in which we can approximate it is, first, we draw a tangent line to the curve, so we have to do the derivative, at a point that we think is close to that root. And then I draw a line from that, or I draw that tangent from that point x, which I think is close to my root, and then f of x naught. So that's this part. So all I've done is I've done the tangent, and I've chose a number that I think is close to what I expect it to cross. It's where I kind of expect it to cross if we're talking about an x-intercept. Then the point from x1 to 0, which is down here, will intersect that tangent line. And that becomes our new approximation. That becomes x1, becomes our new approximation. If we continue to repeat these steps, we're going to get closer and closer and closer to what we believe our root to be. Oh yeah, dang it, Dale. So this is what the process looks like. Here's the formula. The formula is y minus f of our x sub n is equal to f prime of x sub n, and then x minus x sub n. And all this is the point slope form. All this is a glorious version of the point slope form. That's it. Glorious version of the point slope form. We expect my y value to be 0. So if we expect my y value to be 0, then we get this equation. Then we solve for x sub n plus 1, and we get that equation. That's the equation that we use for Newton's method. That's the equation we use for Newton's method. So that's the equation you all need to write down. Yes?
Is x sub n just standing for like changing x, just like
X sub n?
Yeah.
So as an example, if I want to know the first iteration, my x sub n would have been 0, and then x sub n plus 1 would have been x sub 1.
Okay. So it's just
If I want my second iteration, then x sub n would have been x sub 1, and x sub n plus 1 is x sub 2.
so kind of like the same idea as sequences.
Sequences and series, yes. And this is actually a recursive sequence because it's dependent on what I knew from the previous one. Madison.
I'm trying to figure out how those two are incorporated.
Okay. How I got from here to here?
Yeah.
Okay. So let me erase some of this stuff. So if I take this equation, which is 0 minus f sub n, if I distribute this out, right, I'm going to get, on the left-hand side, I'm going to get negative f of x sub n is equal to, and on the right-hand side, I'm going to get x sub n plus 1 multiplied by f prime of x sub n minus x sub n multiplied by f prime of x sub n. I'm solving for x sub n plus 1. So anything that doesn't have an x sub n plus 1, I'm going to move to the other side of the equal sign. So I'm going to have x sub n, f prime of x sub n, minus f prime of x, or f of x sub n. Oh, I didn't want yellow. X sub n is equal to x sub n plus 1, f prime of x sub n, dividing both sides by f prime of x sub n, we get this lovely. So you all wrote down that equation because that's the equation that you use for Newton's method. All right. So moving on. First thing you want to do when you're doing Newton's method is you want to choose one as close as you possibly can get. So if you're doing a polynomial that's larger than degree 4, you can choose some values by using the rational zeros theorem, so pre-calc 1 information. And then if your signs change between two of the values that you pick, then you know there's a root or a 0 between them. There has to be. And so what you can do then is say I've got a root between them, and then I can start doing the Newton's method. But you want to choose a number that is close to it as you possibly can get. Yes?
So we learned just in the previous section to do the min-maxes so we can determine where roots are.
Yep. Once you've chose a number that you think is close to that 0 or the root, then you're going to start using Newton's method up until the point that you stop having changes in your numbers. And what I mean by that is at some point your decimals are not going to change. So once your decimals no longer change, then you know that you probably have the root. Your calculators and Desmos is using Newton's method. So when you plug into Desmos a very large polynomial, or any polynomial, and in fact, it is using Newton's method to give you the x-intercepts. And that's the same thing your calculator's doing. Now back in the day, again, they paid grad students to sit and number crunch. How delicious is that? Okay, so we're going to go through an example of Newton's method. Now, we know this thing factors, right? We can look at that and say, and I know it factors. I know that x squared minus 2x minus 3 factors. We're going to go Newton's method just because it's fairly straightforward on something we know the answers to. We know this thing factors. We know what the zeros are. We know exactly what the zeros are. So I'm going to use Newton's method to determine what my x sub 1 and x sub 2 is, because that's all they're asking me for. They're not asking me to actually go further than that. They're not actually asking me to find the zeros. They're just asking me to find x sub 1 and x sub 2. So on the homework, pay attention to how far they want you to do this iteration. Okay? So you may not have to do it more than 2 or 3 times. It's not going to ask you to do it until you find the answer, because if it asks you on the homework to do it until you find the answer, then you just put that thing into the Desmos and you click on where it's crossing the x-intercept. Because, you know, this is just getting an understanding of one of the reasons why we use derivatives, and that is because it gives us the zeros. Okay, so if I am asked to find my x sub 1 and x sub 2, the first thing I have to do is I have to find f prime. I have to find f prime. So if I'm asked to find this, I have to find f prime first. The reason I have to do f prime first is because that is part of, up here, that is part of what I need on the equation. So that's the equation that you use to do the iterations. So with that information, then the first thing I'm going to do is find my my x plus 1. So my x plus 1 is going to be my x sub n minus my function. All of this right here is just my function plugging in x sub n. That's all I did. And then down here, all I did was I put in to my derivative x sub n. Okay? So this first step, I'm just doing x sub n plus 1. And the only reason I'm doing this at all is so that I can just plug in my numbers that I need, and I don't have to keep doing this over and over again. Because it's x1 and x2, I don't actually need to do this step. I can just plug that information in. But if I have to do several iterations, I'm going to find it generically. And I'll show you what it looks like if you're not doing it generically. So what I'm doing right now is I'm just finding the x sub n plus 1 rule for all of them versus doing one and then doing the next one and doing the next iteration. This next step to go from here to here is I just made a common denominator so that I can add them together. That's all I did. So I took this x sub n over 1 and I multiplied numerator and denominator by the 2 x sub n minus 2. So I could just have a common denominator. That's all I did. Then once I made a common denominator, to go on to this next step is I just simplified the numerator. So now I know if I need to find any x sub n plus 1, all I need is the previous one. I can throw this generically in there and I don't have to keep finding the numbers over and over again. So this is just a generic one. So I'm going to stop. I'm going to have you gaze at the glory of this. And then I want you to ask me questions. So I'm going to just stop here. So I have this explicit sequence defined, and I can start putting in my numbers. So I put in to that explicit sequence, which was this. If I want to find x sub 1, x sub 1 is going to be equal to x sub naught squared plus 3 over 2 times x sub naught minus 2. My x sub naught, they told me, was the number 2. So my x sub 1 is going to be equal to 2 squared plus 3 over 2 times 2 minus 2. And when I do that, I get 4 plus 3, which is 7, divided by 2, 3.2. Now, I want to find x sub 2. So x sub 2 is going to depend on that 3.2. That 3.2 now needs to go back into that equation again. So it'll be 3.2, the quantity squared, plus 3 over 2 times it's 3.5. Sorry, 3.5. 3.5. There we go. 3.5. So 3.5 and then minus 2. So somebody with a calculator, what do you all get? Yes?
Shouldn't it be x sub naught, not x sub 1? Equals that?
The first, this one
Yeah.
here?
No, the one that equals 2. Except that our x sub naught is equal to.
It is. Our x sub naught is 2.
So does that make, since it's x sub naught plus 1, does that just make it x sub 1?
Yes.
Okay.
Yep. 3.05? If I was asked to find the next iteration, And then I would do x sub 3 is 3.05, the quantity squared, plus 3, over 2 times 3.05 minus 2.
3.0036.
No, we'll go with that. Now, as you notice, I'm getting closer to 3. If I wanted to do this again, I would put that number back in. Now, I don't have to find this explicit term. If I don't want to find this explicit term, which does make it easier somewhat, if your algebra skills are cool, then you're just going to use this equation here. So let's redo this using that equation and not using the explicit part. So if I reuse this using x sub 1 and everything else, so my x sub 1 is going to be equal to x sub naught minus f of x sub naught over f prime of x sub naught. Okay? So that's what I'm going to use to find x sub 1 if I didn't find it explicitly. So I still have to find f prime, which is what we did here. So f prime of x is equal to 2x minus 2. x1 is equal to 2, because if you remember over here, my x sub naught is 2, minus, well, I need to put 2 into my original equation, so 2 squared minus 2 times 2 minus 3, all over 2 times 2 minus 2. So I put that in my calculator, and hopefully I get the same answer of 3.5. Check it to make sure that I get 3.5. On the numerator of my fraction, I get 4 minus 3, so my numerator is going to be negative 3. In my denominator, okay, cool. So I get the same answer. Now again, if I didn't do this explicitly, then I'd have to do this again with x sub 2 is equal to 3.5 minus 3.5 squared minus 2 times 3.5 minus 3 over 2 times 3.5 minus 2.
So if you only have 2 terms, you have to solve for it. It's easiest to do that. But if you have to do more than that, it's exponentially takes a lot more time.
Yes. So if you only have to do 1 or 2 terms, then you can just use that formula right here and just put in the 1 or 2 terms that you need. If you were actually trying to go further, like this one, and I'll go back if you're writing it down. If you had to go further, you obviously want to find the explicit formula because that's going to be much, much faster. How is that? Okay. So on this next one, all I want to do is find x sub 1 and x sub 2. You can do it with it explicit if you like. If you're like, man, I love my algebra, you can do it explicitly. If you're like, nope, I'm not fond of algebra, we're not friends lately, we haven't been sneaking out of the house, they don't call me anymore, then just do it by using that formula. It's up to you. If we are asked to find where they intersect, so in this case I'm asking where y is equal to e to the x and y is equal to x to the third intersect, then we can still use Newton's method. The way in which we use Newton's method is that I set these equal to each other and I bring one to the other side to make it equal to 0. So I have these two equations, and I have e to the x is equal to y, but y is also equal to e to x to the third. So I have e to the x minus x to the third is equal to 0. I consider that my function. So I consider f of x is equal to e to the x minus x to the third. Because this is going to ask for an approximate solution, then I'm probably going to have to do more than one iteration. More than 2 iterations, probably 3 or 4 until my decimals stop changing. So in this case, I will have to do the explicit on here. So to do the explicit, the first thing I have to do is find f prime of x. This is going to be e to the x minus 3x squared. My x sub n plus 1 is equal to x sub n minus f of x sub n over f prime of x sub n. So this is going to be x sub n minus, I'm going to go back up right here, and I'm going to put x sub n wherever I see x. E to the x sub n minus x sub n to the third power. My derivative, which is right here, goes in the denominator. And wherever I see in the denominator, I see an x, I replace it with x sub n. So this is going to be e to the x sub n minus 3x sub n squared. I have to have a same common denominator. Right now this is over 1. So I'm going to multiply this by x e to the x sub n minus 3 x sub n squared. So this is going to be x sub n e to the x sub n minus 3 x squared x sub n minus e to the x sub n minus x sub n cubed all over the now the same common denominator. Multiplying that x sub n through, I have x sub n e to the x sub n minus 3 x cubed x sub n minus e to the x sub n plus x sub n cubed e to the x sub n minus 3 x sub n squared. So when I get done, I'm going to have x sub n e to the x sub n minus 2 x sub n cubed minus e to the x sub n all over that denominator. Now I'm going to use that because I know I'm going to have to go more than 2 iterations to figure out what I get. Yes, questions? Yes?
How did Newton come up with this at 23 or something?
Because he didn't have internet.
No, I've got it. Duly noted.
All right, so when you do that, you end up doing a couple approximations. The first approximation gives you this number. Second approximation gives you this number. The third approximation gives you that number. And notice at this point, right here, that, let me scroll in. Notice between here and here, the things that have stabilized is a 0.857. So at that point, we have stabilized to 3 decimal places. And I can do it again, but the 3 decimal places aren't going to change. So it took me 3 iterations to get this one. And that's Newton's method. Have a great day.